Assalamu alaikum, Engineer Mutawwa.
Alaikum assalam wa rahmatullah. How are you? Good?
Alhamdulillah. How about you?
I'm fine. How about everything?
Everything is good. Alhamdulillah. How is Ramadan with you?
Yeah, it's very tough now with work at this time. Yani.
Yeah.
But I finished most of the work yani, for my part. Yani.
Okay. Good. Very good.
Hello,
Assalamu
Assalamu alaikum.
alaikum.
This is Salman Mahmood. How is everybody?
Assalamu alaikum, Salman bhai. How are you?
Yes, I'm good. How are you?
Alhamdulillah. Assalamu alaikum, Dr. Umar. Assalamu alaikum, Dr. Fahad. Dr. Umar, we cannot hear your voice. Can you hear our voice?
وعليكم السلام دكتور سليم.
Thank you, Dr. Fahad, for joining us.
Yeah, it is my pleasure. Are your students ready?
Yeah, they are ready.
Alhamdulillah. Actually, I'll attend just the first 30 minutes because I have a meeting in scientific council. So
Jazakallah for giving us even 30 minutes. Thank you so much.
Thank you for your and for your students.
Thank you, Dr. Shah.
I'm just checking on Dr. Muhammad Umar Siddiqui. If he can hear us, then we will begin. Now I'm just waiting for Dr. Umar to join, and then inshallah ta'ala, the session can start on time. Dr. Umar is giving a message that he has joined the meeting through Zoom, but it's not working properly. So, Dr. Fahad, what is your suggestion? Shall we begin or shall we wait for him?
Is he one of the?
Yeah, he's one of the members. Yes, he's one of the jury members. The external member is also joining now. Dr. Zahir is also joining.
Is Dr. Zahir with us now?
Just I'm checking. He sent me a message that he's joining now.
Okay. I don't know, but it is important that Dr. Muhammad Umar join us. So in this case, what about Dr. Salman? What about Dr. Salman?
Is he here? Dr. Salman is already
here.
here.
Assalamu alaikum, Dr. Fahad. I'm here.
Okay, Dr. Salman, are you a member of the committee?
Yes, I'm a member.
I am looking for one who is not a member, so we can make him a member.
Yes, I'm already a member.
Dr. Nasser
Maybe
is
Dr.
here.
Sajid.
Oh, Dr. Umar came. Just let me check Dr. Umar once again. Dr. Nasser is here. Dr. Sajid is here. Dr. Umar is here. Dr. Alhamdulillah, we have now 13 participants.
Okay, so in this case, if Dr. Muhammad cannot join, we can choose any of our colleagues to be a member of the committee.
Okay. Who do you suggest? We have all of them, Alhamdulillah, here.
But now Dr. Muhammad Umar join us.
Yeah, he joined us, but his mic is not appearing. So maybe I'll send in a message.
Well, I thank you, Dr. Muhammad Umar, for choose this time for your mobile and your laptop, and good time to not work.
Actually, to be honest, this Zoom session requires a lot of graphical power. So if there is a PC which has 4 GB of RAM, will underperform.
Okay, so I think
we have Dr. Tahar, we have Dr. Sajid, we have Dr. Nasser, we have who else we have?
Okay, who wants to be a volunteer?
Assalamu alaikum.
وعليكم السلام ورحمة الله وبركاته.
I can volunteer to be a member in the committee if necessary. Yes, I can be.
Okay. So, Dr. Nasser now instead of Dr. Muhammad Umar.
Alhamdulillah. Okay, Dr. Nasser, I will send you an email with the forms also, with the forms attached that you need to fill up and send it back to me after the presentation.
Sure, thank you.
Okay, so Alhamdulillah Rabbil Alameen, Bismillahir Rahmanir Rahim, As-salatu wassalamu ala ashrafil mursaleen, Nabina Muhammad wa ala alihi wa sahbihi ajma'in. With the permission of the Honorable Chairman of the Department, Dr. Fahad, I would request the permission to begin the session. Shall I begin, Dr. Fahad?
Okay, please start.
Okay. First of all, I am acting as a chairman of the session in the absence of our beloved Dr. Muhammad Umar Siddiqui. I want to thank the committee members. I want to thank Dr. Salman. I want to thank Dr. Zahir, and I want to thank Dr. Umar for participating. And in addition, Dr. Nasser, and all the participants, Dr. Tahar, and all the participants who have joined us, Dr. Sajid also. So the topic of our presentation today is fundamental study related to the development of modular solar panel design for improved durability and reliability. The project has been funded by Deanship of Scientific Research IAU and has been completed by satisfying all the formalities. Now I will leave the floor to the students of the senior design project, Mr. Majdi, to start, or Mr. Muhammad to start with the presentation. Mr. Muhammad, then Mr. Majdi and Mr. Abdul Malik, the floor is yours. You can begin with the presentation.
Okay, thank you, Dr. Muhammad Siddiqui. Assalamu alaikum wa rahmatullahi wa barakatuh.
Wa alaikum assalam wa rahmatullah.
Assalamu
Majdi, share screen, please.
Screen, does screen?
Yeah, the screen is here.
Yeah,
The screen is
clear.
And we can hear you also. You can begin with the presentation.
Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. My name is Muhammad Zafar Qahtani, and today, inshallah, we will present our senior design project, fundamental study related to the development of modular solar panels design for improved durability and reliability. I inshallah start present with my colleagues Abdurrahman Majdi and Abdulmalik Makhaita. This project is supervised by Dr. Muhammad Salim. Nowadays, solar industry is one of the most important industries. But the problem with that industry is the typical design of solar modules. Solar modules are designed as one-time use product with no consideration of repairability factor. Having no method to restore the power losses of damaged modules contribute to the generation of more waste into the environment. Moreover, having a system that is constantly under the risk of permanent power losses is not feasible, especially for remote areas and underdeveloped countries. We have tested our conventional modules under many conditions, and we found that the solar panels are not designed for any kind of repair mechanism. So we have to develop a new kind of solar modules, which is financially more visible in certain conditions as compared with the typical modules. As you can see in the photos, natural disasters such as hailstorms or windstorms can cause damage to the solar panels, whether the crack is visible or invisible. As you can see in the video, crack can decrease the efficiency of solar modules up to the 30%, depending on the size of the crack. Our methodology: testing, then designing, then prototyping. All modules testing was conducted in GCC lab. We started by testing the modules by applying power test to measure the panel parameters, then applying hail test with a different number of hail impact to increase the damage, then detect the cracks. After testing the panels, we found that a new design for a solar panel should be easy to replace in order to eliminate damaged parts of the system. We started with the modular designs and then improve the design over 2 prototypes. I'll leave you with my colleagues Abdul Malik Mukhaita to continue with you.
Assalamu alaikum. Thank you, Muhammad. My name is Abdul Malik Mukhaita. The first step is quantify the damage that can affect solar module. This step was achieved by simulating the hail hits. Hail hits were simulated using pressurized chamber that showed different size and type of falls into certain location on the panel. Power at standard test condition was measured for each panel before and after the impact test in order to compare power losses due to the generated damage. In order to have a visual presentation of the generated crack, an electroluminescence imaging device was used to take photo before and after hail impact test. As shown on the slide, the first photo on the left is an EL scan for the panel before applying hail impact. The next photo is an EL scan for the same panel after the impact, showing damaged cells around the impact location and far from the impact location. 2 modules were tested. The first module with 1 impact showed 8% drop in the power at the maximum power point. The second module with 3 impacts showed 16% drop in the power at the maximum power point. Based on results from destroy the whole panel and leave a permanent power loss. In order to overcome this problem, this design work and introduce a new modular design that increase the visibility of replacing parts of the module to eliminate the parts that are responsible of power loss. The main idea of this design is creating module out of cells that are contained in a small unit. This design allows the module to contain the damage in a small unit that can be easily replaced. The design includes 2 main elements, cell unit and connection element. The cell unit contains 3 parts, top clear cover to allow radiation transmission, solar cell, and at the bottom, thin rigid cover to hold the cell. The connection element consists of 2 parts that hold the cell assembly together from the top and the bottom. Inside the connection, two neodymium magnets to work as joining element that hold 2 cells together. And between the 2 connection parts, a small notch is added for additional supports against torch. The power transfer between cells happens through tapping ribbon that is passed through small grouping in the connection parts. The first prototype, the yellow one, faced the problem with small notch that was designed to pass ribbon to the next cell. We found that the notch was weak point in the design and it break easily if a small torch stress applied to the parts. Keeping that in mind, the second generation was reinforced with bigger notch and fitting element to overcome that stress. And I will leave you with my colleague Abdul Rahman.
Thank you, Abdul Malik. Assalamu alaikum wa rahmatullahi wa barakatuh. I'm Abdul Majdi and I will proceed with the lifespan analysis of the design. To compare the lifespan of a typical solar system with a solar system based on a modular design, we need to take into consideration 3 main aspects: the material and cost, the damage cases that can affect the system, and the last one is the payback analysis. Starting with the materials that was used to manufacture the design, most of the materials were locally available. The only material that we needed to order online was the tapping ribbons. They were not locally available. After considering these materials, we found that the cost of 1 cell unit will be around $11, around 40 riyals, compared to conventional or typical solar modules, which 1 cell will cost around between $4 to $7 to make. We considered 3 cases that usually affect the performance of solar system. First case is hail impact damage with 30% system damage and 70% system damage. Second case is thermal degradation with 50% system damage and 90% system damage. Last case is mechanical stress due to transportation between two locations, and this case is detailed in the report. Starting with the first case, the damage due to environmental factors such as hail impact. We considered a typical system that has 10 modules. Each module contains 36 cells, and to make an equivalent system based on a modular design, the power output of the system that is based on a typical design. In case of a 30% system damage, we will have 3 damaged modules with a total of 108 cells, and on the other hand, with a modular design, we will have only 3 cells damaged that needs to be replaced. For a 70% system damage, we will have 7 modules damaged with a total of 252 cells to replace, compared to only 7 cells within a modular design. The financial aspect of this case shows that we can save up to 90% in the replacement cost to restore the damage. Average solar module price $250 compared to only $11 per unit for a modular design. The second case, which is a thermal degradation. Thermal degradation is a condition that can affect cycling between high and low temperature during the operating hour during the day. And in this condition, the solar cells, instead of generating electricity, it dissipates the generated electricity in a form of heat. In a 50% system damage, we will have a total of 5 modules damaged and a total of 180 cells damaged, compared to only 36 damaged in a modular design. In a 90% system damage, we will have a total of 9 modules that include 324 cells that is damaged and needs to be replaced, compared to only 36 cells that needs to be replaced in a modular design. We can see that both percentage, 50% and 90%, has 36 cells, but in this case, the damage is the same amount, but the problem is the damage is more scattered around the system. The financial aspect of this case shows that we can save up to 68% in replacement cost for 50% damaged system, and save up to 82% in replacement cost for a 90% damaged system. Now we can summarize the main differences between modular and typical solar modules on three main aspects. The possible damage. The typical module will completely damage from one impact, where the modular design the impact will damage one area, and the damage will be contained on a one cell area or detaching. The power loss on a typical module, the power loss will be permanent and cannot be recovered. Modular design, the power loss is temporary and can be recovered by replacing only the damaged part. The replacement pattern, in a typical design, we need to replace the whole panel, and compared to only replace the damaged parts on a modular design. In order to make both systems equivalent, we consider the following assumption in payback analysis. Both is the expected lifespan for a solar system. The failure or the damage will be introduced to the system in the midlife point, which is around the 12th year. Both systems will have system will have the same power output, working hour, weather condition, and billing rate. And in the last, all costs other than the capital cost of the project are eliminated from this analysis. In the first case, with the hail impact damage and 70% replacement, we can see that conventional system reaches the break-even point earlier than the modular system, and this is due to the fact that the initial cost of a modular system is higher than a conventional system. But after introducing the damage into the system, we can see that the conventional system took a huge drop in order to recover from the losses and the damage that happens, compared to only a small drop for a modular system design. And it actually, and in this case, the modular system design is more feasible than a conventional system design, because it introduces more profit during the following years after the damage. The same applies for the second case, the thermal degradation with 90% replacement cost. We can see that the conventional system reaches the break-even point earlier than the modular design due to the difference in initial cost. But after introducing the damage to the system, the modular solar system recovers better than a conventional system due to the low cost of replacement to recover from the damage. And I will leave you with my colleague Mohammed Al-Qahtani to proceed with the conclusion.
Thank you, Abdurrahman. In the conclusion, we introduce a new modular design for solar modules. The design is proved to control and reduce the system damage. And also the design is reducing the waste generation to the environment. The new design reduces the replacement cost. With the reduced replacement cost, with the insurance premium will be much lower. The modular design is financially more visible in certain conditions compared with the conventional modules. For the future works, we need to conduct more experimentation, since we were not able to finish the experimental work due to COVID-19. Also, the selection of material is an important part of the future work. And inshallah, we are aiming to applying for US patent and submitting a paper. This project was funded by Deanship of Scientific Research, Imam Abdurrahman bin Faisal University, with the project ID 2019-112 engineering. And this project has been completed by satisfying all technical requirements and stipulated by the university. And finally, we want to express our thanks to the Deanship of Scientific Research and Imam Abdurrahman bin Faisal, to Dr. Fahd Al-Amri, who helping us always, to Dr. Nasser Hariri, who guide us and during the prototyping process, to Dr. Umar Siddiqui for his valuable advices, to Engineer Ijlal for helping us during the experimentations, and we were hosted by DCC Lab. We would like to express our thanks for him, especially Engineer Nawaf Al-Ahmed and Engineer Firas Al-Dosi. Thank you.
Thank you so much, Mr. Abdul Malik, Mr. Mohammed Al-Qahtani, Mr. Majdi, for your presentation. I request the floor is now open to all the participants in case if they have any questions or suggestions. I request you to make the presentation in a more spread form using a Windows view, the second view on the right. Yeah, this one. Yeah. Zoom out so that all the slides are visible. Yeah. So the floor is open to all the members who have joined our session. In case if they have any question, then please guide us with your valuable comments. Okay. Is there any question from the audience regarding the presentation? Okay, I request the floor now to be open to the jury members, especially Honorable Dr. Zahir, who is our external supervisor, who is our external jury member, Dr. Salman, who is our internal jury member, and Dr. Nasser Hariri, who is our internal jury member. If you have any questions or suggestions for improvement or areas where you think that they can change the direction, I request you to please give us your feedback. The floor is open for your comments.
Assalamu alaikum. I might start. I have one question. In fact, two questions. So the first one is actually, how big is the thermal degradation issue that solar panel systems are facing, or are as a damage? If we consider thermal degradation, how big is that issue for us? That's my question. The second question is, so far you show us a very nice design for increasing the sustainability of the solar system, right? By just having these new modular designs to replace the traditional ones that we have. What will be the cost, the potential cost for these? Because when we saw, I think in one of the slides, let's see, I think slide 22 or 21.
The cost of the design.
Yeah, just
right.
Let him finish the questions. Write down the questions, and then one by one you can answer. Dr. Nasser, please, the floor is yours.
So if we go to slide, I think 21 or 22, the payback of your new design or modular design is started at lower cost, minus 4,000. Why is that? Does your modular design cost more, and why is that? From just looking to the structure of your modular, right? You are using the same cells, you are modifying some of the elements that can be easily manufactured. And I don't see why there is almost double the starting cost for the two systems. In fact, you can bring your modular design cost, your initial value, closer to the traditional one. That's give another advantage to your system. So these are the general two questions I have.
Thank you for the question, Dr. Nasser. Regarding the first question about the thermal degradation, the problem of the thermal degradation is that only one cell affected with the thermal degradation can affect the whole performance of the panel, because usually the cells and the panel connected in series, and when the current reaches the infected cell, it starts to dissipate all the current that generated in the previous cells in the form of heat from that cell only. So the problem with this type of damage is that it can appear. It's not we cannot expect the behavior when it can appear, and it needs to be diagnosed with special equipment, because the cell visually looks the same as any other cell. It needs an infrared camera to be sure that this cell is infected with thermal degradation and it's dissipating the power instead of generating the power. Regarding the second question about the cost, in this table here, we listed the local the materials that we used and the materials that were available locally. And these materials, we consider the use of these materials is not highly efficient, because these materials were used in a developing process, not in a mass production process. This is why in the future work we mentioned that we need to work more on the material selection. We believe that with better material selection, the cost of the design will be lower, yes, and it will perform better in the payback analysis.
Majdi, assalamu alaikum.
Wa alaikum assalam wa rahmatullahi wa barakatuh.
Yes, Doctor. So one by one, I will request now, Dr. Farooq. I'll come back to you after the question of Dr. Tahar, and then after that, I'll leave the floor to Dr. Fahad. Dr. Farooq, I see your hand. I will inshallah ta'ala come back to you after this one. Yes, Dr. Tahar, the floor is yours.
Sorry for contributing before the jury's member, but just I will join also the comment of Dr. Nasser by going to the slide number 21. Before everything, I would like to thank Majdi and all the group members for the great job and the great work done during this sim design project. And thanks for their advisor, Dr. Salim. Regarding the question, my question here in the y-axis, what I am seeing cost, but I think this is the cumulated cash flow cost here in the y-axis. Not just to mention cost, because it makes the figure confusing like happened with Dr. Nasser, because once you will make the cumulated cash flow cost, you can see better the figure, you can comment the figure better, and you can judge here which my question is, I can see from this figure that the payback time for the conventional panel is exactly 50 or 51 months. However, for the modular design payback time, it's about maybe 76 months. Means that the payback time for the conventional panel is shorter than the modular design payback time. This is my first comment. However, later after maybe 120, 30 or 36 months, the accumulated cash flow becomes of the modular becomes more important than the normal panel. My question is, when I'm following these two trends, I cannot see how the accumulated cash flow cost of the modular design or the introduced design in your SDP becomes more important once you will integrate over the whole month periods. I don't think so that the accumulated cash flow of the modular becomes more important than the conventional panel. Can you answer, Majdi, or anyone?
Sorry, doctor, to be sure from your question, you say that the payback behavior of modular system is, you want us to explain if the payback behavior of the modular system is better from the conventional system after introducing the damage to the system?
Yes, first of all, the payback time of the conventional panel is approximately 51 months. However, for the modular design payback time, it is about 76 months, which means that the payback time of the conventional module is shorter than the modular design payback time. Is this clear? Or is this?
Yes, this is clear. But
خلاص طيب. However, after the month of 130 or 32 is not mentioned here, the payback time or the related cash flow becomes more important for the modular. Means that it becomes more worthy after this critical month.
Right.
Yes, once you will integrate for this gain from this month till the end of the lifespan of the module, is that integration will recompensate what has been lost from 0 months to 120 or 32 months?
Okay. For the break-even point, as I explained in Dr. Nasser's question, this break-even point hugely depends on the initial cost of the cell, because our design initially costs better. One cell is cost around $11, where on the conventional design it costs $4 to $6. This is because the selection of the materials. We worked with the available materials to us, but we believe that we can choose better materials that can lower the cost, and by result, it will improve the the period, the system it takes to reach the break-even point.
Mhm.
And regarding the overall system and cost analysis, I believe if we choose better materials, yes, if we integrate over the whole period of the system, the modular design will financially perform better than a conventional system.
Also, Doctor, I have answer. Doctor, actually, the impact or the damage can happen at any time. We can't control when the impact or the damage happened. So this is assumption that the damage will happen after 10 years. So if it comes earlier, that means our modules will be better than the conventional module.
Yes, very convinced the answer. Thank you, Muhammad.
Okay. Dr. Nasir, I see your hand. I will give the floor to Dr. Farooq because he's waiting, and then I'll come back to you. Dr. Farooq, the floor is yours, sir. Dr. Farooq, the floor is yours. Your question?
Can you hear me now?
Yes, yes, we can hear you now.
Yes.
Okay, sorry, it was on me. Okay, actually, I had the same question, but I just want to help the group. Okay, if you look at this, and we did this in the renewable energy about cash flow and cumulative cost. Obviously, in this slide, payback analysis, there's something that's missing. And that's why, if you look at this, it is clear that the conventional is far superior cost-wise. I mean, it has a payback time which is much earlier, and then the cash flow, like Dr. Tahir pointed, is the accumulation. So if you add or integrate area under the curve, definitely the conventional system payback is superior here. What's missing? My question is, you guys have done a very good job, but you have missed something that's not reflected on this chart. Give me the answer, and I will give you 100%. There's one thing missing in this chart that will make your curve go up than the conventional system. What is that reason? Or what is that you are not showing? And you have talked about this in your report, and you have your justifications. It's just that those justifications are not reflecting here on this chart. And if you can show it, definitely you will see that the modular design curve will go up. So what is that's missing in this chart? And I think we talked about briefly during renewable energy when we did the cost analysis, the payback, and all that stuff. So there is one thing missing here.
If you allow me, Doctor, to take a guess, maybe you are talking about the insurance, the cost of insurance, and how to replace the.
Yes, you're coming there. Replace. Okay. What you are not showing is that the damage that will cost the conventional system. Now, in this curve, you must also include the damage cost. So if you include, and in the analysis, you have shown that you save 90% or 65% based on the different damages. I'm pretty sure that if you include those damages, the blue curve will go up. And if you can show that the cumulative cost at the end of the day on considering these, you can look at the statistics, maybe you can get an idea. What is the, for example, replacement cost of these panels? After how many months you need to replace all these panels? So if you put that in, this cost is going to dip. And so what you really need to show is that the dips in the modular one are going to be less as compared to conventional. And so overall, the conventional curve will go below and so at the end, what the investor usually is looking at your cumulative cost and your payback period. So I think we covered this in the course. So if you can show here that, okay, you can consider like the scenarios you considered. If you consider those scenarios and put them here and say, let's say your whole system, because of one storm or something, 30% was damaged. So show that here, like, okay, after 3-4 years, we had a major event. And now, that's how you can really show that, because this is what you're doing. You're trying to say that it's more cost effective to have the modular. So you need to show that here on this chart that, when you have damages and, that the costs then go up. So what you're showing is an ideal curve here. And instead of the ideal curve, you need to show an actual, scenario in which you have damages. And so then the cost curve is not a straight line. It's haphazard. It goes up and down with damage. You have to cover the damage. You have to cover the maintenance. And so there are so many other factors. So in reality, this curve is not a straight line. It is you can say spiky, like going up and down, up, it's wavy. And so if you put that model that you have showing that 95% or 65% of the time, this is more, if you can somehow put that cost in there, then you will definitely see that your modular design is superior. Okay, because if you just show this, nobody is going to believe that your modular design is superior. Here, definitely it's going to cost more, and the payback is longer. And there is nothing in this curve that gives an indication that this is modular. So my advice is, if you can show, think of the same scenarios that you have talked about, put that into this cost analysis also, and then really see that, okay, does the modular really pay back as compared to conventional? And that will be more convincing to the audience. And I think that's the reason everybody's looking at it, because it's clear that you are not incorporating the damage part in this curve. So if you do that, inshallah, you'll see that the modular curve will go above the conventional one. Okay, so that's something that I just wanted to point out.
Okay, thank you, Doctor.
Thank you, Doctor, for the advice.
We are ready for doing all of that, inshallah.
Thank you so much, Dr. Farooq, for your valuable comment. Hi, Dr. Zahir, I got your hand. I will now leave the floor open to Dr. Nasser, and then I will come back to you. Dr. Nasser, the floor is open to you, sir. After that, I will ask
thank
Dr.
you.
Zahir.
Yes, again, thanks for all the members. I have my last question here. It's a very interesting project and very interesting design that came up. So let's go to the picture or the slide for the design itself. Maybe slide 8. Yes. So my question is there any wastage or losses in the overall generated electrical power compared to the traditional modules? In other words, is there any waste on the overall area of the solar cells due to the additional gaps that you introduce in your new design, right? So if you look into the normal PV panel that we have, solar cells are very close to each other, and we don't have that introduced gap due to this design. So now, as you build a module that consists of many cells, and you compare your new design with the same area of your traditional PV panel, what will be the losses in power and electrical power of your new design? That will also come back to your payback chart again, will affect your payback chart. So how much is that introduced wastage of area between the cells will affect the overall power? That's another criteria that can be investigated also in the future of this project. But I just want to highlight it, and maybe if you have something to comment in this, that would be great.
Yes, we can confirm that this considering this design will use more area, and this definitely will impact on the electrical behavior of the system. But we can say that this design can be more optimized to use less area. Because, for example, we have built an edges around the cell here that can be eliminated later on. But we were unfortunate to be unable to complete our tests regarding the power output of this module due to the fact that we were not able to be on the campus anymore.
Great. Yeah, just my last comments is that you might need to compare the output of the electrical power of the new design after you optimize it, you reduce that area with the traditional one, and then from that you can see how efficient is your system compared to the traditional one. In terms
we had that in plan, but we couldn't proceed with the plan due to the current circumstances.
Yes, understood. Great. Thank you so much.
Thank you, Doctor.
Thank you, Doctor.
Thank you so much, Dr. Nasser. Now the floor is open to Dr. Zahir for his valuable comments.
Assalamu alaikum.
Wa alaikum assalam.
Assalamu wa rahmatullahi wa barakatuh.
Thank you very much. I first want to appreciate you guys and your supervisor, Dr. Salim, that you have done really a great job. Considering that you are the undergrad students, you have really done a valuable thing. My comments could be more towards the layman person. So if I'm not clear about something, any one of you can clarify about that one. First, my question was, which Dr. Nasser just asked you about the efficiency of your new design and the conventional panel. I was a little bit doubtful about the power output, but it's already clarified. The second question is also about the payback analysis. If you could show me that slide. The slide which shows the payback analysis.
Oh, this slide.
Yeah, here I had the question which is already clarified, that if you integrate it over the lifespan of the new design and the conventional design, maybe the conventional design will be on the superior side. But in this particular case, you have introduced only one-time damage during the whole life. How do you have some statistical data that how many times these solar panels get damaged during their life? And what about the case that if you introduce more than one time these damages to the panels, and then you do the cost benefit analysis, and you can give some threshold that this is the life, this is the number of damages after which this new design becomes more beneficial as compared to the conventional design. Is there something like that?
In fact, on actual cases that we were lately part of a webinar that talks about the damage on real power plants, this photo is one of the photos that they used. They stated that sometimes the damage in the system or the insurance claim of the system can triple just because the damage is not visible. When they conducted a general analysis of the system, they claimed an amount of insurance, and then after again analyzing the system with EL scanners to see the damage inside the cells that is not visible, the claim doubled, tripled in value.
Yes.
And the system can sometimes completely, we introduced 30%, 70%, and 90%, but in real cases, the whole system can be damaged from one start.
Okay. My question was that you have introduced the damage only once in the life of the solar panel, right?
Yes, that is correct.
Yes.
One-time damage.
Okay. So if your damage is more than once, for example, after repair or after replacement, it happens again, then maybe if you introduce more than 1 points, then it will be more prominent that how your system is better than as compared to the conventional system.
Mm-hmm.
Yeah, that's a very valuable
Yes,
point. It's exactly what he's trying. Guys, let me explain. What he's trying to say is that in your case, you have introduced only one damage, and you have shown that your modular panel becomes more economically feasible as compared to the other one. Imagine that there's on the same site there is a second hailstorm after 1 month. Okay. Then again you will have an enriched in case of a traditional one, you will have to replace the whole site again, but in your case again very minimum damage. So when you will have multiple damages on the same site, it means that your solution will become much more economically effective. So in terms of larger more damage cycles, you will become much better. That's what he's trying to say to you.
Okay.
Correct, sir? Correct, Dr. Zahir?
Yeah, exactly.
Thank you, Doctor.
Okay, I have a couple of questions here. If
Yeah,
Dr. Zahir is done.
no, Dr. Zahir, is any other question?
Thank you, I'm done.
Okay. Now I leave the floor open to Dr. Salman, because Dr. Salman, we didn't hear anything from him yet. Dr. Salman, please, the floor is yours in case if you have any questions or suggestions for our guidance.
Okay, thank you, Dr. Salim. Okay, first of all, this is a good project and the students have done a great job. But again, my concern is regarding the which Dr. Nasir already mentioned about the power issues. And students have mentioned that they don't have the time to do the power calculations due to this COVID-19. They are not going to the university. But what about the initial calculations? In one of the slides you have mentioned that the efficiency with some crack or something, the efficiency is decreased by 30%. Right? So have you calculated this amount, that how much big is the crack, and how, according to that, how much the efficiency is decreasing or something like this? Did you do any analysis in the initial phase that when actually the efficiency is decreasing due to the damage?
We actually, in the beginning of this semester, we conducted the experimental work in the GCC lab where we took real panels and hit them with bolts to introduce damage to the module. And here we can see that the power with increased number of hits, the power loss increases. And these are experiments that we conduct. I will leave the floor for Muhammad if he can add to that.
Yes. For the 30%, we were in some webinars, we were participating in some webinars, and there is a company who's evaluating the micro cracks outcomes. I meant when there is a micro cracks, how is the huge of the decreasing in the efficiency? So this he was saying that the expert was saying that the micro cracks depend on the size of the crack. It can reach to up to 33%. This is what I'm heard from you about the 30%. This is from the expert from ELPV magazine. There was a webinar, so we were participating with them.
Okay, so you heard this term from him?
Yes, from him, an expert.
But you don't have any evidence or any proof in the published literature about it?
In the literature we have it, but this is our numbers as you see in the table. Module 1, this is our number.
8% and 16%.
And it increases with the with more damage to the panel.
Yeah, let me see this. Okay, so this is basically, you have mentioned here the voltage and current and power before and after.
Correct.
And what is this FF percentage?
This is the fill factor.
What is this actually? Is it related to the power?
The fill factor compares.
Majdi, Majdi,
yes,
please
doctor?
explain the whole table. Explain the whole table so that all the audience is clear. All the audience can maybe that it is not clear. Yeah, make it bigger size and explain the whole table, please.
Sure. And the first table here, the VOC and the open circuit voltage and the short circuit current are the voltage and the current that is generated from the panel with no load on the panel. On the other columns, the maximum point voltage and maximum point current. These are the voltage and current at the maximum power point that the panel generate. And this is multiplying both these values will generate the maximum power point here. And the fill factor is a term that is used to describe the performance of a PV panel by telling how much can the panel generate energy from the available energy, from the maximum possible energy that can be generated. And yes, so these are the factors. This factor is a ratio between the maximum power divided by the maximum possible, which is the multiplication of open circuit voltage and short circuit current.
The maximum possible over the maximum from the
maximum output over the maximum possible.
All right. So basically, you are just testing it for the extreme boundary conditions. That's why you are taking the open circuit voltage and short circuit current, because voltage is maximum in that case and current is maximum in that case.
Yeah. Standard test condition.
All right. Fine. So basically, in the beginning, you have done this test that this much power is lost, but you have not done any test after your repair that how much power is back actually. That the powers which was lost initially due to this damage, when you repair that damage after the repair, that this much amount of power is back.
The problem is that we cannot repair a typical module. This is why we introduced our design. In our design, if the design takes one hit, the damage will be only contained in the area of one cell only, not scattered. Like this panel was only hit one time at this location, but we have damage here and here and the rest of the panel. This is why we introduced our design. In case of the design of the cell takes a hit at this part, there is no physical path for the crack or for the damage to proceed for other cells connected in the system. So the initial problem of this research that there was no way that we can repair a damaged module, a damaged solar module. This is why we introduced this design.
Okay. Okay, fine. So you have only done the this cost analysis for your design, not the power analysis, right?
Yes, we couldn't make the power analysis.
Yes.
Okay, but that is actually very important that you should do the power analysis for your design as well.
Yes, Doctor, it wasn't the plan, but
for this design, maybe for the future work, because if, for example, your design is not as efficient as the other one, as the regular design is, then obviously, if you will give this design for no cost, nobody will buy this design, right? If it is not providing you that much power. So before doing the cost analysis, the first thing is to do the power and efficiency analysis for the design. All right. If that is providing that much power, or that is providing, for example, 75% of the power, that is providing 50% of the power, right? Then you can say that, okay, this cost is low, and even it is providing 75% of the power as compared to the regular design, or it is providing 50% of the power that's compared to the regular design, but it is providing less power. That's why the cost is also low. All right. Or if it is providing 100% of the regular power, the same amount of power, and if the cost is low, that would be the ideal case. But the cost analysis must come along with the power analysis. Basically, power analysis should be first. After that, it comes according the cost. Basically, if you go to any of the design, first is the working and then the cost analysis.
Yes, doctor, I completely agree with you. But
Yes.
the problem is that the power analysis and the experimentation for power analysis was in the plan, but we could not proceed with that plan because we cannot.
Yeah, I'm just
be in the
suggesting for
campus.
maybe the future work more. This is because
Sure.
the power analysis is also very important.
Sure.
Okay, right.
Thank you for
very
the
much.
advice. Thank you, doctor.
Thank you, Doctor.
Thank you so much to all the jury members. Dr. Zahir, your mic is open. Is there any question that you wish to give us?
No, thank you very much.
Okay. So now we are almost coming to the end of our session. It's almost 1 hour, 2 minutes less than 1 hour. We are 58 minutes now, now 59 minutes. So now I want to first of all thank our honorable jury members, Dr. Salman Mahmood, Dr. Nasir Hariri, Dr. Zahir Kazmi for their valuable comments and feedback. And we have noted down all the questions, and rest assured that inshallah ta'ala action will be taken in the future in order to incorporate that. Furthermore, I want to thank individually Dr. Fahad, Dr. Tahar, Dr. Farooq for their valuable comments. And in case if there is any other feedback, you can just feel free to send us an email to help us improve the future of the work. Again, if there is no question, then I want to thank all of you again for participating in our today's session. And I request the honorable jury members to please send me email me the forms so that the further process of these students can be finished. I thank you all for participating, and now I will end the meeting. Congratulations, guys.
Thank you, Doctor.
Thank you.
Thank you, doctor.